Okay, so because we already late 5 minutes, I think it's good time to start. And yeah, thank you everyone for coming today. And this is our fourth lecture, and we still have 3 more again every Saturday except during Hari Raya Idul Adha. So for the last one, we skip 1 week. I think we can start right now. Maybe Professor Erfanian, please.
Yes. Okay, just let me share a screen. And so can you see my slide?
Yes, very clear.
Yes.
All right. Okay. So
Oh.
okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, all of you. But here we have in the morning. So thank you very much for just attending to my lecture. It's my fourth lecture, as I mentioned. So I'm going to deliver some lectures on algebraic graphs. So as I mentioned last week, so we divided in 3 parts. We finished part 1. In part 1, we introduced entities and some graphs associated to groups or even ring. In the second part, which we start today, we have 2 lectures, today and next week. So in these 2 lectures, I will talk about the spectra graph theory in algebraic graphs. And the second part, I will mention something about topological indexes in, again, algebraic graphs. So we are mostly using algebraic graphs. So today we will deal algebraic graphs through spectral graph theory. First of all, let me remind some matrices, which is important in this lecture. The first thing which I'm interested to mention here is to talk about the generalized inverse of a matrix. You know, we have the inverse of a matrix, but if we are talking about the inverse of a matrix, we have to make sure that first thing, the matrix is a square, so we don't have inverse for example, m times n matrix. So we have a square matrix and also the inverse. But here I'm going to define the generalization of inverse of a matrix, which is not necessarily a square and not necessarily the determinant is not 0. So let me define the generalized inverse of a matrix. So suppose that A is a m times n matrix. That's the size of matrix. As you know, it's not necessary to be a square. The generalized inverse of matrix A is n times m matrix. So look at here, A is m times n, but the generalized inverse of A is n times m. So, you know, we just change the size of rows and columns. So the generalized inverse of A is n times M matrix we may denote by B such that we have this condition. So A times B times A is A. If we have this condition, then we can say that B is the generalized inverse of A. Let me give some examples. The first example we just explain inverse because if A is n times M invertible matrix, so I would like to say that A inverse is a special case of the generalized inverse. So if A is n times n is a square matrix and it's invertible, so we have A inverse, and we can see that A inverse is the generalized inverse of A because A inverse satisfying this condition. A inverse A is A inverse is the identity matrix, and times A is A. So it means that A inverse is the generalized inverse of A. Now, let me give another example for the generalized inverse. So look at A. A is not a square, it's 3 times 4 matrix, right? The generalized inverse of A, so we may denote the generalized inverse, we can say G inverse for shorten to say generalized. So we say G inverse of A is matrix B. B is 4 times 3 matrix. So A is 3 times 4, but B is 4 times 3. And we can easily check that the condition that the ABA is inverse of A. Okay, let me give some notes here. Snyder, is everything is okay? Because
Yes, we can hear you.
You can hear and see everything?
Yes.
All right. Okay, so if we got problem for this corner, just let me know because
Okay.
I'm using share screen, so I can't see it, the connection is okay or not. All right, let me give some notes. The first thing is that, as I mentioned, if A is invertible, right? So A inverse is the generalized inverse. Is but so it's not necessarily B is invertible because you know that the first difference is that B is not necessary to be the same size. The A square because to be a square. Even if they are a square, so it's not necessary. If A has G inverse, then A has inverse. So you know that if A has A inverse, so A inverse is G inverse, but the converse is not true. The second note for the G inverse is that for every matrix A, we can easily show that the G inverse is always exists, but there is a little problem that the G inverse is not necessary to be unique. And we may have more than one, or sometimes we may even infinitely G inverse for matrix A. For example, look at matrix A. This is a column matrix. It's for that each of matrices B1, B2, B3, B4, all of them are G inverse for A. So we may also have many many other J-inverses for A, because what we have to do, we have to take a 1 times 4 matrix with 4 entries, and if the sum of 4 entries is 1, then the matrix is unique. Now, we are interested to, when we are talking about the matrix and the property of a matrix, so we are interested to have a unique of that matrix. So here we may mention one of important matrix, which is very important in linear algebra or even in operation research, right? So the matrix is Moore-Penrose inverse of a matrix. Let me define the Moore-Penrose inverse here. Suppose that A is M times N matrix, right? The Moore-Penrose inverse of A is N times M. You know, A is M times N, but the Moore-Penrose inverse is N times M matrix B, such that we have the following conditions. So look at the conditions here. The first condition is that ABA is A. So the first condition says that B is the G inverse of A. But we should have 3 more conditions. So we should have BAB is B. So here is A is also G inverse of B. And the 2 other conditions say that AB is symmetric. So the transpose of AB is itself. And similarly, BA is symmetric. So BA transposition is BA. So if we have these 4 conditions, then we can say that B is the Moore-Penrose inverse of A. Right. It's usual to denote the Moore-Penrose inverse of A by A plus, the Moore-Penrose inverse of A by A plus. So if we use this notation, we can see that the above 4 conditions, right, is that A plus A is A. So here is A plus is G inverse of A, and A plus A plus is A plus. So here is A is G inverse of A plus, and A plus and A plus A, both of these 2 matrices are symmetric. So this is the definition of Moore-Penrose inverse. For example, suppose that A is 3 times 4 matrix, right? Now, the Moore-Penrose inverse of A is 4 times 3, and it's this matrix. So you can check the above 4 conditions for A plus. Now, one of important theorem about the Moore-Penrose inverse is that if A is M times N matrix, and of course, if the Moore-Penrose inverse exists, because it's not necessary to have Moore-Penrose inverse for every matrix. Sometimes it's not exist. So if A plus exists, then the Moore-Penrose inverse of A is unique. So here, it's guaranteed that if we have more than one Moore-Penrose inverse, the proof is easy, and just I would like to mention that if we have more than one Moore-Penrose inverse, for example, if B and C are two more penrose inverse, then we may use 4 conditions for B, because B is the more penrose inverse of A. So we have 4 conditions for B and 4 conditions for C. So we have 8 conditions that we can use for the proof. So if, for example, here we start with B, so we can say that B is BAB, because A is the G inverse of B. That's the second condition. And also you can see that is equal B, we can put AB by AB transposition, because AB is symmetric. And you know that we can put AB transposition is the B transposition A transposition, right? So if we use these 8 conditions, then we can reach to C. So here we show that B is C. So it means that we have only one more Penrose inverse. So the more Penrose inverse is always unique. This theorem is also the way how to compute the more Penrose inverse for A. So if A is a matrix, the rank of A is this or columns. So if the rank of matrix A is R, then we can give the composition for A as a product of 2 matrices, B and C. B is M times R, and C is R times N matrix. And here we can compute more Penrose inverse of B and C here. And if we compute B plus and C plus, then A. So in this way, we can find the Penrose inverse of A is an easy way. For example, look at matrix A is 3 times 4 matrix. We can easily check that the rank of A is 2. And here we give 2 matrices B and C. B is 3 times 2 and C 2 times 4. And we can easily check that A is the product of B and C. Use B plus and C plus. So the more Penrose inverse of A, or just A plus, is the multiplication of C plus and B plus. Now, let me give just introduce another matrix. Suppose that T is a tree. You know that tree is a connected. Every tree, we have 2 conditions. First one, tree is a connected graph, and secondly, we don't have any cycle. So we can just easily see that if we have a tree with n vertices, then the number of edges is n minus 1. So if we have a tree, so we at least, because tree is connected, so we at least need n minus 1 edges. And because T has no cycle, so n minus 1 is the utmost edges. So the number of edges is exactly n minus 1, right? Now, let me give the definition of path to a vertex I. We denote the path matrix for path I for a tree is a square matrix is n minus 1 times n minus 1, right? Matrix, the rows and the columns are indexed by the rows are indexed by ages. So we have n minus 1 age here, and the columns are indexed by vertices, but we have to remove the vertex I here. So the columns are indexed by 1, 2, for example, here, I minus 1, I plus 1, and n. So we have n minus 1 columns and n minus 1 rows. Right. Now, for each column, so if we, I'm going to define the path matrix for and to introduce each column. So if you take vertex j, right, j as a column, in columns we don't have I. So if we take j, and if you take the path between from j to I, for 3 we have a unique path. There exists path from every vertex to another vertex, and it's unique. So the path between vertex j to I, we may denote by tja. Is a vertex. Now we are going to determine the column j. Column j related to ages, right? So if we take the row t, row et, just the row related to ages et, so we can put this entry is 1 if this age belongs to the path from j to I, and the direction is the same. You can see that here we are talking about a directed graph. We have simple graph, so we don't have loop and any multiple edges, but the graph is directed. And we may put -1 if still the edge is in the path, but with opposite direction. And if the edge is not in the path, we may put 0. Let me give examples here. So consider the following 3. We have 6 vertices and we have 5 edges. Now, I'm going to determine the path matrix P5. 5 is one of vertices. So for P5, you know that here we have 5 edges here for P5, and columns we have 6 vertices, but we have to remove 5. So the columns are 1, 2, 3, 4, and 6. Now look at the column, first column. First column, we have 1. So we have to consider the path between 1 to 5. If you look the tree from 1 to 5, we have a path here by 1, it consists only one edge, E1, and E1 has opposite direction. So here we have -1 because the direction is opposite, and we don't have E2, E3, E4, and E5 in the path, so we have to put 0. And for the second column is the path between 2 from 2 to 5, and from 2 to 5 you can see that it consists only edge E3. We can put just 1 for the rows corresponding to E3, and the rest are 0. And similarly for column 3, 4, and 6. For example, for column 3, we have to consider the path between 3 to 5. From 3 to 5 consists of 2 edges, 4 without the column 3 because it's in the path, and the direction because E4 has opposite direction, and for the rest is 0. So this is the path matrix, is P5. Now, in the just next few minutes, I will introduce the inside the matrix because I defined right. So I'm going to define inside this matrix and give a relation between path matrix and just inside this matrix. First of all, I need to define inside this matrix. You know, in these 2 lectures, I will introduce some matrices which are associated to a given graph. Now, let me define the inside this matrix. If gamma is a directed simple graph, so we have direction and the graph is simple, means we don't have any loop or multiple edges. So if we have, so we have n vertices, right? And we have m edges. The inside this matrix of graph gamma, we may denote by the notation Q of gamma, right? And it's n times m matrix. So the rows are indexed by the vertex set, but the vertices 1 to n, and the columns are indexed by edges. So the inside this matrix is n times m matrix. N is the number of vertices and m is the number of edges. Now, the entry, ij entry of inside this matrix, right? Because you know, I is associated to vertex I, and j is ej, right? So if vertex I is one of n edges, one of n vertices of ej, right? Maybe because ej has a direction. So if I is in the initial vertex of ej, we will put 1, and if j is the terminal vertex, is the end vertex of ej, we will put -1, and if I is not any vertices of ej, we will put 0, right? Let me give example to be more clear for you. Look at the graph gamma here. We have 5 vertices and we have 6 edges, right? So the vertex set of gamma is 1, 2, 3, 4, 5, and the edge set is E1, E2, E3, E4, E5, and E6. Now, the inside this matrix is 5 times 6 matrix because we have 5 vertices and 6 edges. Look at here. The first column, if you look, the first column is related to edge E1. If you look E1 is an edge from vertex 2 to vertex 1. So we have to put for the row associated to 2 is 1, because 2 is the initial vertex, and we put -1 for rows associated to vertex 1, right? And the other is 0. So here for E1 is from 2 to 1. So we have to put 1 here for vertex 2 and -1 for vertex 1, and the others are 0. And for E2, as you can see here, E2 must be an edge from vertex 1 to 3, because we put for vertex 1 and -1 for 3. And E3 is an edge from 4 to 1. You know, look at E3. E3 is a vertex from 4 to 1. So for vertex 4, 1, and for the row 1, we can put -1. So you can see here, this is the inside this matrix of graph gamma. You know, here gamma is just directed simple graph. So maybe gamma is 3, or maybe it's not 3. We may have so any arbitrary graph gamma. Now, one of the important matter for inside this matrix is the rank of matrix. As I mentioned earlier about the rank, when we are talking about the rank of a matrix, is the right. Now, it consists of two components. So X is not connected. So we have 5 vertices here, right? And we have 4 edges. So the inside this matrix of graph X is 5 times 4 matrix, right? So the rows are indexed by these 5 vertices, 1, 2, 3, 4, 5, and we have 4 edges as the columns. Now look at the first column, E1. E1 is an edge from vertex 2 to vertex 1. So for vertex 2, we put 1, and for vertex 1, we will put -1, and the rest are 0. For edge E2, the second column, E2 is a vertex, is an edge from vertex 3 to vertex 4. For vertex 3, we may put 1, because that's the initial vertex one. That's the other 2 columns. So this is the inside matrix of graph X. Now, if we compute the rank of the inside this matrix of graph X, so the rank is 3. You know, the inside this matrix of X, graph X is 5 times 4 matrix, but the rank is 4. It is 3. And for gamma, for the inside this matrix of gamma, it's 5 times 6 matrix, but the rank is 4. There is a very nice theorem to say that if gamma is directed and simple graph with n vertices, so we have cases. If gamma is connected, then the rank of this matrix is n minus 1. And if the graph is not connected, and you can see that the graph X, number of vertices is 5, so 5 minus the number of components, 5 minus 2 is 3. So the rank of inside this gamma has 5 vertices and it's connected, so the rank is 5 minus 1 is 4. So this is important theorem about the rank of incidence matrix. Now, if we compute the incidence matrix for a tree, you know, if gamma is a tree with n vertices, so we know that the number of edges is n minus 1. So the incidence matrix of gamma is n times n minus 1 matrix, because we have n vertices and n minus 1 edges, right? Now, if we remove one of rows in the incidence matrix of a tree, for example, if we remove the row number n, then we will get a square matrix n minus 1 times n minus 1. And we can prove that this square matrix, just the square matrix by removing one row from the incidence matrix of a tree, this matrix is invertible and is not singular, right? So this is very interesting to see that if we remove one of rows of the incidence matrix of a tree, then we can get invertible matrix. For example, here is a tree, right? So we have a path P5 with this direction. So the incidence matrix of this tree is 5 times 4 matrix, right? Because we have 5 vertices and 4 edges. This is the incidence matrix. Now, if we remove one of rows, for example, if we remove row 5, then we can get 4 times 4 matrix, right? And you know the rank of this graph is 5, because the graph has 5 vertices and is connected, so the rank is 5 minus 1 is 4. Now, if we remove one of rows, for example, here you can see I remove row number 5, and the second one is we remove row number 4, and so on. So that's all these square matrices are invertible. Now, let us come back to path matrix, which I mentioned earlier, right? Now, you can see that I defined the right. Yes, I defined the path matrix for a tree with respect to vertex number 5. This is the path matrix. Now I'm going to give a relation between path matrix and the incidence matrix. This is the theorem which give a very interesting and useful way to compute the inverse of as I told you, if we remove one rows from the incidence matrix of a tree, then we can get invertible matrix. So what's the inverse of this matrix? That gives a relation between path matrix and just the inverse of incidence matrix by removing one rows. So suppose that T is a tree, and we have n vertices. So if Q is the insiders matrix of T, and Q sub J is the reduced insiders matrix, which we can obtain by deleting rows J of Q. So the Qj is invertible. Now here is exactly Pj is the path matrix with respect to vertex J. So, you know, if you compare computing the inverse of Qj and also computing the path matrix, you can see that computing the path matrix Pj is much easier than to compute the inverse of Qj, because if we have many vertices, so the size of Qj is quite big and is not easy to find the inverse. But the path matrix is very easy, and just we can compute Pj by definition which I mentioned to you. Let me give example to just explain more about this relation. Suppose that T is a tree. So we have 6 vertices and we have 5 edges. The inside this matrix of Q is 6 times 4, 6 times 5 matrix. We have 6 vertices, so we have 6 rows, and we have 5 columns because we have 5 edges. And here is the interest of inside this matrix. For example, if you take the second column, E2, so E2 is an edge from 5 to 4, right? So we can put 5 is 1 and 4 is -1. The rest are 0. So this is the inside this matrix. Now, if we remove the row number 5, right? So Q5, we remove the row number 5. Row number 5, we have 1, 1, -1, 0, 1. We remove the row number 5. So that's the Q5. Now, as I mentioned, Q5 is an invertible matrix, right? Because the rank of this matrix is 4. Now, we have already find, or we can just find P5. That's the path matrix. Path matrix, you know, we have 5 edges, and on the columns, we have 6 vertices, but we should remove the vertex 5. So we have 5 times 5 vertices. This is the P5. Now, it's not difficult to find P5. And here, the most important is that the inverse of Q5 is P5. So we can compute the inverse of Q5, not necessarily by a direct way, but we can use the path matrix P5 to just find the inverse of Q5. If we remove, for example, row number 4, so the inverse of Q4, so Q4 inverse is P4. So note these two, we have the row number 5 in the inside this matrix, and here is path matrix with respect to vertex 5. So this is the relation between path matrix and the reduced inside this matrix by removing one row. So as an example, as an exercise. So we have n vertices. As you know, all vertices are adjacent. Now we may put a direction for Kn. The direction is that the vertex I is adjacent to J if and only if I is less than J. So for example, if we have 5 vertices for K5, so we have direction 1, 2, 2, 1, 2, 3, 1, 2, 4, 1, 2, 5, and 2, 2, 3, 2, 2, 4, 2, 2, 5, and similar. So that's the direction. Now, the first question is how is complete with directed complete graph Kn, right? And the second is that to find the more Penrose inverse of Q. You know, Q is not necessarily a square because we have, for example, if you take K4, right? For K4, we have 4 vertices and we have 6 edges. So it's a 4 times 6 matrix. So compute the more Penrose inverse of Q. Anyway, let me move the inside this matrix. Right. Now I'm going to define the second matrix associated to a graph. The second matrix is similar to inside this matrix, but it's the graph is not necessarily directed. So we can define the inside this matrix for any arbitrary graph, not necessarily directed. And we can mention by 0, 1 inside this matrix. So if gamma is a graph, so as you can see, it's not necessary to be directed. So if we have n vertices, so the vertex set is 1, 2, up to n, and the edge set is E1, E2, EM. So we have n vertices and m edges. The 0, 1 inside this matrix of gamma, we may denote by m of gamma, is again n times m matrix, and we can define it as the following. So if you take vertex I and HEJ, so row and column, so the entry MIJ we may denote by this definition. So if the vertex I is not belongs to is not one of 2 ends of EJ. So if I is not belongs to the HEJ, we may put 0. And if I is one of n vertices of EJ, so here it is not necessary to be initial or terminate vertices because we don't have direction. So in that case, we may put 1. So the difference between the 0, 1 inside this matrix or the 0, 1 inside this matrix, so we may put 1 terminate vertices. But for inside this matrix, we can put 1 for initial vertex and -1 for the terminate vertex. So it means that if the inside this matrix, we replace -1 by 1, then we can get the 0, 1 inside this matrix. Here is K4, right? So you can see that we have 4 vertices and we have 6 edges. Now, the 0, 1 inside this matrix is the following. So we have 4 vertices and 6 edges. So the 0, 1 inside this matrix is 4 times 6 matrix. Now look at column 1. Column 1 corresponds to HE1. If you take E1, E1 is an H between 4 and 1. So it's not from 4 to 1. So because we don't have direction. So E1 is an H between vertices 4 and 1. So we can put 1 for vertex 1 and vertex 4. And the rest are 0. For example, if you take column number 4, which is associated to HE4. E4 is an H between 3 and 4, so we can put 3 and 4. Here is 1 for 3 and 1 for 4, and the rest are 0. So this is the 0, 1 inside this matrix. Now, one of interesting 0, 1 inside is 0 if n is even and 2 if n is
Oh, okay. So I think, yeah, he get disconnected. Yeah.
Memang putus-putus adik Tuhan.
Yeah. So I'm sorry, Professor Erfanian. So I think there is a problem with the connection. Yeah.
Nggak dengar ya?
Iya. Belum di mute.
Is that okay?
Yeah, yeah. Right now it's okay.
Can you hear me?
Yes. Right now we
All
can
right.
hear you. Okay.
I don't know. Today we may have maybe just low speed for the in 0, 1 inside this matrix of a cycle Cn of length n. You can see that we have only two values for the determinant of this matrix. We have 0 if n is even and 2 if n is odd, right? Now, the rank of 0, 1 matrix is also interesting. So if the gamma is bipartite graph, right? So the rank is the same as the rank of inside this matrix is n minus 1. And if gamma is not bipartite, so the rank of the 0, 1 inside this matrix is n. You can see that the rank of inside this matrix is always n minus 1. But here is a difference between the rank of non-bipartite graph. So the rank of 0, 1 inside this matrix is 1 if gamma is not bipartite, but the rank of inside this matrix is still n minus 1. And here you can see that the rank of 0, 1 inside this matrix of complete graph Kn is 1 if n is 2, and for n is bigger than or equal to 3, we have n. And here is for C4, right? C4, you can see that C4 is bipartite graph. So the rank is 4 minus 1 here is 3, just by this theorem. Now, let me move to one of very, very important matrix in a graph. So we are mostly using the third matrix here for just some of results in algebraic graph. So this matrix is very important. And the importance of this matrix is that, first, let me define the matrix and then compare with the inside this matrix. So the third matrix, which is associated to a graph, is adjacency matrix. So suppose that G is a matrix for this graph. Suppose that gamma is a graph with n vertices. The adjacency matrix of graph gamma we may denote by A of gamma. A is the first letter of the word adjacency. So that inside this, the adjacency matrix of gamma, A gamma, can be defined with the following conditions. Right. So the adjacency matrix is a square matrix. The rows and columns are indexed by vertices. So we have n vertices. So the size of adjacency matrix is a square matrix is n times n matrix. Now look at row I and column J. So the entry Ij we can define as two cases. If you take two vertices I and J, so if I is adjacent to J, so we will put 1, and if the vertex I is not adjacent to J, so we can put 0. So the adjacency matrix is 0, 1 matrix. So all entries are 0 and 1. So not any more than 0 and 1. Now, there are some properties of adjacency matrix. The first one is that the adjacency matrix is a symmetric matrix. You know, so that if I is adjacent to J, so the entry Rij is 1. Vertex J is adjacent to I. We have so Aij and Aji are the same, and that's because if I is adjacent to J, so obviously J is adjacent to I. So the adjacency matrix is a symmetric matrix. Now, if you take any fixed row, for example, if you take row I, so if you take row I, so in row I we have some zeros and some ones. So how many ones actually we have? You know, the number of ones exactly is the degree of y, the degree of I, because the degree of I is the number of vertices which are adjacent to I. So if vertex I is adjacent to 5 vertices, or if the degree I is 5, so it means that we have 5 1 in row I. So the number of ones is exactly the degree of I. Now, the third properties of adjacency matrix is that In the diagonal, we have 0, because if you take vertex I, so I is always 0 because we don't have loop. The vertex I cannot be adjacent to itself. So all entries on the diagonal are 0. Now, because the adjacency matrix is a symmetric matrix, so we have n real eigenvalues. You know the definition of eigenvalues, so just I can refer you to linear algebra book. So since the adjacency matrix is symmetric, so we will have n real eigenvalues. So if we put eigenvalues by lambda 1, lambda 2, and lambda n, so that's all eigenvalues of adjacency matrix, and they are all real. And the next one is that the sum of eigenvalues are 0, because we can easily prove that the adjacency matrix of gamma is similar to a diagonal matrix with which enters on the diagonal are eigenvalues. Now, the next result for the adjacency matrix, if we consider the multiplication of two distinct eigenvalues, right? So the sum of lambda I, lambda j, with I is less than j, and they are between 1 and 1. This summation is the minus number of edges. And for the triple products of eigenvalues, so the products, the sum of products lambda I, lambda j, lambda l, for I less than j, less than l, between 1 and n, is 2 times the number of triangles of gamma. This is some elementary properties of adjacency matrix. Now, suppose that gamma is a graph with n vertices, and lambda 1, lambda 2, and lambda n are all eigenvalues of gamma. You know, when we say the eigenvalues of gamma, it means that the eigenvalues of the adjacency matrix of gamma. So we don't mention specifically adjacency matrix, just say the eigenvalues of graph gamma. But actually the correct sentence is that the eigenvalues of the adjacent matrix of graph gamma. Now, the spectrum of gamma, we can denote by aspect of gamma this n eigenvalues, lambda 1, lambda 2, and lambda n. The spectrum of gamma is the set of lambda 1, lambda 2, and lambda n. Now, you know that when we are computing eigenvalues for a matrix, sometimes some of eigenvalues are the same. In this case, if for example, if 2 is one of eigenvalues, if we have three eigenvalues equal to 2, we can say that 2 is an eigenvalue with multiplicity 3, right? So now, if we consider all distinct eigenvalues, so if lambda 1, lambda 2, and lambda k are distinct eigenvalues, of course, with multiplicity m1, m2, up to mk, right? So it means that lambda 1, we have M1 eigenvalues equal to lambda 1, M2 eigenvalues equal to lambda 2, and so similarly, Mk eigenvalues equal to lambda k, right? So here, by this notation with multiplicity, we can give just a shortened presentation for the spectrum of gamma. So the spectrum of gamma is lambda 1 to the M1. So to the M1, that's the upper upper of lambda 1, M1 means that lambda 1 we have M1 lambda 1. So lambda 2 to M2 and lambda k to Mk, and for the spectrum of the gamma, and you can see that it must be the number of vertices is n, right? So this is the spectrum. Now, from now on, I would like to move to algebraic graphs, but before that, let me give the spectrum of some known graphs, and then we can just move to algebraic graphs and combine a spectrum with algebraic graphs. Now, if we have complete graph Kn have to n eigenvalues. So the eigenvalues of adjacency matrix Kn, or just eigenvalues of Kn, we have -1, so we have n minus 1 eigenvalues, and n minus 1 with multiple equal to, so the spectrum is, we have one eigenvalue equal to n minus 1 and n minus 1 eigenvalues equal to minus 1. So we have n minus 1 eigenvalues -1. For example, if we 1, 4, 4 minus 1 and 1, 4. Now, how about the complete bipartite graph K and M? We should have n plus m because the number of vertices of K and comma m is n plus m vertices. So we have to determine n plus m eigenvalues. Eigenvalues of complete bipartite graph K and M, we have 0 with multiplicity m plus n minus 2. So 0 with multiplicity m plus n minus 2, and one of them is a square root of m times n and minus the square root of m times n. So the spectrum of complete bipartite graph K and M is 0 with a square root of m n with multiplicity 1 and minus a square root absolute root with multiplicity 1. Now, how about the cycle? If we have a cycle Cn, right? The eigenvalues, so we should have n eigenvalues. The eigenvalues of Cn is, we can denote by lambda sub k, equal to 2 times the cosinus of 2n. For k is 0, 1, 2 up to n minus 1. So we have, for example, lambda 0. Lambda 0 is 2 times cosinus of 0. 0 is 1, so lambda 0 is 2. 2 cosinus of 2 p over n, and so on. So we have n eigenvalues here for cycle Cn. For the pass Pn, we have again n eigenvalues, and the eigen is 2 cosinus of p times k over n plus 1. Give eigenvalues first. Sometimes we can use the Cartesian product, and we can use the eigenvalues for the Cartesian product in terms of each eigenvalues of each of graphs. First of all, let me define the Cartesian product. So suppose that we have 2 graphs, gamma 1 and gamma 2. So the vertex set of gamma 1 is x1, x2, xn. So we have n vertices for gamma 1, and the vertex set of gamma 2 is y1, y2, ym. So we have m vertices for gamma. So we may denote by gamma 1 notation is a graph. The vertex set is the set of all ordered pairs xi, yj, which I is between 1 and n, and j is between 1 and n. So we have mn vertices for the Cartesian product. Now, h between any of 2 vertices is x order pair x, y, and x prime, y prime. So we can say that these 2 vertices are adjacent if we have one of these 2 cases. If x is equal to x prime and y is adjacent to y prime in gamma 2. Or we have y is equal to y prime and x is adjacent to x prime. The first entry or the second entry must be equal, and the other entries we should have an h in the just corresponding graph. This is the definition of Cartesian product. Here are some examples for the Cartesian product. For example, the Cartesian product of K, the product of K2 and between them we have K2. We have 2, we have K2. So the Cartesian product of P3 and P4. So because we have P3, we have 3 vertices. So we have 3 copies of P4 and 3rd copies. So we have 3 copies of P4 and we have 4 P3, 4 copies of P3, right? And for Cartesian product of K2 and C4, so we have 2 copies of C4. You can see by color blue, and we have 4 times of K2 that's shown by red one. This is the Cartesian product. Now, Here is very interesting theorem about the eigenvalues of Cartesian product. So suppose that we have gamma 1 and gamma 2 as two graphs with vertex set. The gamma 1 has n vertices and gamma 2 has m vertices. Now, if A is the adjacency matrix of gamma 1, because gamma 1 has n vertices, so the adjacency matrix is n times n matrix. And if B is the adjacency matrix of gamma 2 has m vertices, so the adjacency matrix of gamma 2 is m times m matrix. So we have n eigenvalues for gamma 1 is lambda 1, lambda 2, and lambda 1 are all eigenvalues for gamma 1. And because B is m times m, so we have m eigenvalues for gamma 2. So if mu1, mu2, and mu_m are eigenvalues for mu2, now the eigenvalues for the Cartesian product, gamma 1 and gamma 2, is lambda I plus mu j for all I between 1 and n and j between 1 and m. So it means that we will have n m eigenvalues for the Cartesian product. For example, we know that K2 we have two eigenvalues, -1 and 1, right? Now, how about the eigenvalues for, so by the above formula, we have 4 eigenvalues for K2 Cartesian product to K2 is 0, 0, 2, -2. And by direct way, you can see that K2 Cartesian product to K2 is C4, and C4 is equal to K2 2. And the formula for the eigenvalues for K22, we have 0, 0, and minus square of 4 is -1. So you can see we have the same eigenvalues.
I think
Terpental deh kayaknya deh.
terpental. Iya. Okay. Already log in again.
So can you hear?
Yeah, I think you just disconnected.
All right, so I don't know what happened. So let me again. So can you see? It's
Yeah.
90?
Yes. Okay.
All right. Okay. So union of two disjoint union of two graphs. So if we have two disjoint graphs, gamma 1 and gamma 2. So if gamma 1 has n vertices and gamma 2 has m vertices, so we will have n eigenvalues. First of all, let me define the union of two graphs. We may the vertex set is the union of just vertices of gamma 1 and gamma 2, and the H set is again the union of for gamma 1 and gamma 2, right? Now, if n eigenvalues lambda 1, lambda 2, lambda n, that's the eigenvalues for the adjacency matrix of gamma 1. And since gamma 2 has m vertices, so we will have m eigenvalues for gamma 2. Now, the spectrum of gamma 2 is mu1, mu2, and mu-m. So the spectrum of gamma 1 union gamma 2 is the union of spectrum gamma 1 and gamma 2. So that's the set consists of all n eigenvalues lambda 1, lambda 2, lambda n, and all m eigenvalues mu1, mu2, and mu-m. That's the spectrum for the. So that's important, because if we have disconnected graph, so we may have some connected components. So for each components, we may find eigenvalues for the adjacency matrix of that components, and the union of all eigenvalues are the spectrum or the set of all eigenvalues for the just whole graph. Now, here we can use our previous lectures on algebraic graphs and combine with a spectrum. I will give us some examples here. Example number 1 is the conjugate graph for symmetric group S3. You know the definition of conjugate graph. Conjugate graph, if we have a group G, so the vertex set for conjugate graph is the set of all elements of G. And if you take two elements, X and Y, we can say that X is adjacent to Y if and only if X and Y. We can say that X and Y are belong in the same conjugacy classes, right? So S3 has 6 vertices, right? So the vertex set for conjugate graph of S3 consists of 6 vertices, right? Now, conjugacy class of S3. Conjugacy class of S3, we have 3 distinct conjugacy classes. The first one is the singleton set of identity as the first conjugacy class, and the second conjugacy class consists of all cycles of length 2, right? Consists of 1, 2 class, consists of 2 cycles of length 3, 1, 2, 3, and 1, 3, 2. And here is the graph, the conjugate graph of S3, right? So we have a singleton, just isolated vertex for identity 1. We have a triangle for vertices in the conjugacy class. This is the second conjugacy class 1, 2, 1, 3, 2, 3. And here we have an H between 2 cycles of length 3. So the conjugate graph of S3 has the following graph structure is K1 union of K3 union of K4, right? So we have 3 components. Now, the spectrum for K1 is a isolated vertex, so the spectrum is 0. We have 1, 0. For K2, for K3, that's the second component. For the K3, we have -1 with multiplicity 2 and 2 with multiplicity 1, right? And for K2, we have -1 with multiplicity 1 and 1 with multiplicity 1. Now, the spectrum for eigenvalues in the same set. So, 1. Now, look at for -1. We have -1 for the spectrum of K2, so the total of them is 3. So -1 with is, so we have 1 plus
Yeah, disconnected. Okay. Sepertinya memang masalah ini ya, betul-betul koneksinya.
Ya, dari tadi terus ya.
Iya. Oke.
So,
Yeah.
can you hear me?
Yes. I think just get this two connected again.
All right.
I don't know what's wrong.
So, can you see my slides?
Yeah.
Yes.
Like,
Yeah.
All right. So sorry that I don't know what happened. We disconnect. Right. So the second example is again, I consider conjugate graph, but for group S4, for the symmetric group of order 24. Now, what we have to do is to determine the complete conjugacy class of S4. Now, you can see that we have 5 conjugacy classes for S4. The first conjugacy class is a singleton, so the set consists of identity elements. The second conjugacy class consists of all cycles of length 2. So we have the third conjugacy class consists of all cycles of length 3. So we have 8 cycles of length 3. And the fourth conjugacy class consists of all elements or permutation, which is the multiplication of 2 disjoint cycles. So we have 3 disjoint cycles of 2 cycles of length 2, 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. And the last, the fifth one is the conjugacy class of all cycles of length 5. So we have 6 class. So the graph structure for the conjugate graph of S4 is the union of K1 union of K6, K1 for the first conjugacy class, K6 for the second, consists of all cycles of length 2, union of K8, that's the conjugacy class of all cycles of length 3. Union of K3 for the multiplication of 2 cycles, right? All cycles of length. Conjugate graph of S4, 6 K.
Oke. Sepertinya kita tunggu saja.
I don't know what happened. Is that
Disconnected.
I don't know this. Yeah, I don't know. There's something wrong here.
Or do
We
you
have
want
to check.
turn off your
But not
video?
now. Maybe after about. I don't know what happened. So
Do you not? Do you
is
want to
that
turn off
is
your
that clear, slightly?
Yeah, that's clear. Maybe by turning off your
Sorry?
video will help.
Okay.
Sometimes it helps. Turning off the
Oh,
video.
okay. Maybe that's because that's right. So let me.
Yeah, okay.
Well,
Hopefully that's better. Hopefully. Oh, malah disconnect ya.
okay. Let me.
Yeah, looks better.
Okay. Can you hear now?
Yes,
Can you hear?
yes, yes.
All right.
Okay.
Okay. So all right. The spectrum of the conjugate graph for S4 is the union of the spectrum for K1 and again K6. So if we take the union of these eigenvalues, then we can get 0 with multiplicity 1, minus 1 with multiplicity 19, 2 with multiplicity 1, 5 with multiplicity 2, and 7 for multiplicity 1. This is the second example. Now, I gave you 2 projects. This is the project number 3. Now, the question is that find a spectrum for the conjugate graph of Sn for all n is at least 3. You know, I computed for n is 3 and n is 4. Now, what we can say about the in Sn in general case? Now, let me give another example to this graph. I would like to deal with the dihedral group of order 2 times n. You know, dihedral group of order 2 times n can be generated by 2 elements, A and B, with this relation. So A has order n, B has order 2, and we have a relation BAB is A inverse. Now, you can see that we have 2 times n elements of this group. We have identity A square, A to the n minus 1, B, A square, B until A to the n minus 1B. Now, what we have to do is to find the complete list of conjugacy classes. So we have to, because depending on n is odd or even, then the center is trivial or center has elements of 2 is a subgroup of order 2. So we consider 2 cases. The first case is if n is odd. If n is odd, then the set of conjugacy classes are the following. So we have the conjugacy class for A. We have A, the inverse of A is n, A to the n minus 1. And we have A squared, A to the n minus 2. And until A to the n minus 1 over 2 and A to the minus n minus 1 over 2. Right? And the last conjugacy class consists of all elements B, A, B, A squared, B, A cubed, B, A to the n minus 1B. So the structure of conjugate graph for dihedral group of order 2 times n is the union of K1 is we have n minus 1 over 2 times K2. You know, we have, you look at here, you know, we have 1 K2 here, 1 K2 here. So we have n minus 1 over 2 K2 and union of Kn for the last classification, conjugacy class. Now, the spectrum of conjugate graph of dihedral group of order 2 times n is the union of a spectrum of K1 and n minus 1 over 2 times of a spectrum of K2 and a spectrum of Kn. So if you take the union of them, then you will get this eigenvalues 0 with multiplicity 1, minus 1 with multiplicity 3 over 2 times n minus 1, because you know here n is, if n is odd, so n minus 1 is even, so 3 over 2 times n minus 1 is an integer, it's a positive integer. So 1 with multiplicity n minus 1 over 2 and n minus 1 with multiplicity 1. Similarly, if n is even, then we may have some more conjugacy classes. So we have, again, a conjugacy class consists of identity elements. And here A to the n over 2 is in the center. So we will have, again, a singleton set consists of A to the n minus n over 2. And we have A to the n minus 1, A squared, A to the n minus 2, and A to the n minus 2 over 2, and A to the minus n minus 2 over 2. And we have another 2 conjugacy classes. Here B, A squared, B, A to the 4B, A to the n minus 2 times B, and AB, A squared, A cubed, B, A to the 5B, and A to the n minus 1B. So the structure for conjugate graph of dihedral group of order 2 times n for n is even, we have 2 K1 and we have n minus 2 over 2 K2, and we have the spectrum of the union, the spectrum of the conjugate graph of dihedral group of order 2 times n for n is even. We have 0 with multiplicity 2, minus 1 with multiplicity 3 over 2 times n minus 2, and 1 with multiplicity n minus 2 over 2, and n over 2 minus 1 with multiplicity 2. So I have given 2 research problems. So the first, by the same method, we may find the spectrum for of generalized quaternion group Q4N and for semi-dihedral group def. Let me give maybe one time. Okay, the next example is for the non-commuting graph, so it's better to start
Sorry.
later in the next week, and we may question. So
Yeah.
thank you very much. So in the next week, I will continue about the spectrum for some other algebraic graphs, and then we will introduce the energy of a graph and some more matrix like Laplacian matrix and Laplacian energy and so on. Okay, so if there is any question or comments, so I'm here to give answer.
Okay, thank you, Professor Ahmad Erfanian, for sharing. I think for us, some of us, I think for the matrix related to graph theory, there's, yeah, some of us already know about it. So that's really review what we have learned before. And especially for me, for the spectrum part, I think that's new for me. Maybe any question from another participant? Winda,
Yeah.
maybe.
Yeah. So let me start from a question from me, and maybe the other participants will follow with other questions. Yeah, Prof. Erfanian, thank you very much for the nice presentation. It is new for me. And I would like to know is, first, what is the motivation of the definition of path matrix you explained in your beginning of your presentation? You explained about path matrix when you construct a certain matrix. I mean, from graph, you construct a certain matrix and you call it path matrix. So what is the motivation behind this definition? I just like to know it.
Okay. As I mentioned, if you consider the incidence matrix, right? Incidence matrix for a tree is n times n minus 1 matrix. As I just mentioned earlier, if you delete one row from the incidence matrix of a tree, we will get an invertible n minus 1 times n minus 1 matrix. The point is that how to find the inverse of this reduced incidence matrix. So the usual way is that we can just find by a direct way to find the inverse. But as you know, if the size of matrix is quite big, it's very difficult to find the inverse of matrix. And even in the computer, it's so difficult, and it takes many times to find the eigenvalues, the inverse of, for example, 100 by 100 matrix, right? It takes many times to compute that. And sometimes you have to, you should have more memory to compute this in the computer. No, if you replace computing direct way of inverse matrix by a path matrix, in path matrix algorithm in the computer. So you don't need to take more times for computing the inverse of reduce inside this matrix. We can use path matrix. So path matrix is very easy, not necessary to deal with more times in the computer. You don't need more capacity for the computer. So it's much easier to find the inverse of the reduce inside this matrix by path matrix. That's my motivation. Of course, we may have some more application of path matrix, but we have to think and check them. That's my motivation.
Thank you.
Yeah, okay. Maybe another question.
I have a question, Kak Uha.
Okay.
Yeah. Okay, thank you very much, Professor Erfanian, for the presentation. I have a question concerning about the matrix in general you have presented before. Do you have like a hint how we should give arrange the vertex name so that the metric is quite nice enough or in the form? Yeah, I mean, what is the form is quite tidy or something, so that we are easy to see the properties and so on. I imagine when we give like a wrong meme in the vertex, then it will give maybe like a matrix that matrices that are not quite easy to see or something. Do you have explanation for this? I mean, could you explain us or give a hint for us for this? Thank you very much.
All right, thank you for about this fields. You know, the motivation of introducing some matrices to get up is that we may have different. If you are talking about the graph, so you may just assume some properties in a graph. But when you associate a graph to a matrix, now we have a matrix. In matrix, we have some more properties in the matrix. For example, as I mentioned, we may talk about the rank of matrix. If the matrix is an arbitrary size, and if the matrix is a square, so we may talk about the eigenvalues. So we have many things about the matrix story, and the point is that we may find some relation properties, or even in linear algebra properties and graph properties. So that's the point. So if we are able to find some more relations between graph properties and the matrix properties, so it means that well, we are successful. Of course, there are some application of matrices associated to graphs. For example, I don't have more time to mention. For example, you know that it's is important for a graph to check that do we have a cycle or not. It means that if we have many vertices, so how to check that the graph is tree or forest, depends on connected or disconnected. So finding a cycle is is important. Now, we may check by inside this matrix. If we have inside this matrix, so we have some columns, right? We have M columns associated to M edges. No, if we have K columns, right, which are not independent, it means that it's not linearly independent. Then, in this case, we will have a cycle, or equivalently, if all columns are independent or linearly independent, then we don't have a cycle, to check that do we have a cycle or not. Now, similarly, inside this matrix, we have to check that what we can say about the columns is that all columns are linearly independent or not. No, that's some relations between some properties in graph, and if we want to check something in graph, we can translate to matrix and check the similar condition in matrix. And the matrix is important because if you not defining a graph in computing science is much difficult. But if you want to define a matrix, it's much easier to define in the computer. So sometimes for checking something in graph theory, we can translate to matrix and checking in matrix through computer. So that's another motivation. Of course, we may have some more application of matrix theory in graph theory, which we will mention maybe later about the energy of a graph and something like that.
Thank you for the explanation, Professor.
Okay. Any more question, maybe? Okay. Or if not, maybe I would like to ask about your explanation before, because you mentioned that when we transfer into matrix, it is easier to check using computation, right? Because I'm new in graph theory, so I would like to ask what kind of software that usually being used to do this kind of computation?
Well, we have some softwares which you can access. Two of importance are MATLAB and yes, we can, and Maple. I think Maple and MATLAB are of two important softwares, and they are very strong. Of course, we may have some more other softwares like Mathematica and so on. But I think MATLAB and Maples are more strong for something between linear algebra and corresponding to graphs. Yes.
Oh, okay. Yeah, I also use Maple to count some linear algebra. So it's more about linear algebra, right? For the software.
I have one question.
Yeah.
Prof. Erfanian.
Yes, that's right.
Okay.
About the spectrum, the best spectrum of matrices. Here the matrix is adjacency matrix. Yeah, you have adjacency matrix, and then you compute spectrum. Can we also do it for another kind of matrix?
Yes, in the next week I will explain about the Laplacian matrix, and we will have just a spectrum for the Laplacian matrix, and also we have distance matrix, and similarly we have eigenvalues or a spectrum for distance matrix. Yes, we have different kind of spectrum related to adjacency matrix, but we have something more. I will mention two of them next week, inshallah.
Yeah. And what can we do after we know about the spectrum? I mean, what is the information we get if we know the spectrum of kind of matrix?
Yes, one of importance of the spectrum is to find the energy of a graph. Energy of a graph is the sum of just absolute value of all eigenvalues. So we have some motivation about the energy of graph coming from chemistry, right? So for some graphs, knowing the energy is very important in chemistry. Another motivation for the eigenvalues is that sometimes by the knowing about the biggest eigenvalues, we may denote by lambda 1, and we may check that is that the graph is regular or not. For example, if we have only three distinct eigenvalues for a graph, then we can see that the graph is regular or not. We have some condition about just giving some relations between eigenvalues, number of eigenvalues, distinct eigenvalues, biggest eigenvalues, the smallest eigenvalues to other properties in graph theory.
Thank you. Yeah, I have maybe read in somewhere that there is a chemistry graph. Yeah, maybe you know about this. Yeah.
Yeah, you know, we have some graphs coming from chemistry, because if you see in chemistry, we have a structure for molecule. For example, if you take molecule for example, what we can say, for example, we have H2O. We have two hydrogen and one oxygen, right? So if you draw the related graph is a past P3, because we have oxygen in the middle and two hydrogen from both sides. So it takes P3, right? So we know P3, but this comes from the chemistry. And sometimes we have, for example, CH4 for some molecules, right? So we have 4 carbons and 1 hydrogen. So is the star graph K14. So we have some graphs which are important in chemistry. If you see some journals in mathematical chemistry, you will see some papers related to application of graph theory in chemistry and conversely.
Thank you for your explanation.
Yeah,
I think it's enough.
I think enough for I think it should be enough for Q&A session, or maybe for the last one.
You are so tired by my lecture.
It's very
But the good thing is we can review a lot of things that we already know, and then we also learn some new things. That's really make us very happy. Very excited also. Yeah, I think no more question. So yeah, again, thank you very much to Professor Ahmad Erfanian for sharing with us again for today. And please, for all participants, we will meet again next week. So we have 3 lectures. So next week, next week, and then we have Hari Raya Idul Adha, and yeah, we skip that Saturday. So we jump to 16th of July after that. So I think that's all. Thank you very much and see you again. Yeah, thank you.
Thank you very much.
Thank you very
Okay.
much.
Thank you,
Thank
everyone.
you very much.
See you
So
and see you.
Thank
hope
you.
to meet you next week, inshallah.
Next
Okay.
Inshallah.
Bye.
Inshallah.
Inshallah.
Bye. Bye-bye, everyone.
Bye.
Terima kasih semuanya.
Terima kasih semuanya. Terima kasih.
Assalamualaikum.
Salam.
Salam.
Okay, thank you.